So yesterday we introduced the notion of dual vector space. So specifically, we said that in order to be able to understand the extensions of dot product and inner product of vectors, we need to be able to define not just objects that look like column vectors, but also objects that look like row vectors. And obviously, since these are different kinds of objects, they have to live in different kinds of linear vector spaces. And we call, in general, one of them the vector space and the other as dual to the vector space. So in case of vectors, it is actually very clear that row vectors and column vectors are different kinds of mathematical objects. But following on a couple of questions I received from you directly and also over email, let me also give you another example. So let us recap. So there is an LVS and there is a dual LVS. Okay, and the way I introduced LVS was to request you to think of this as being composed of column vectors 1, 2, 3, and this as row vectors 1, 2, 3. But notice that this is just one example of a linear vector space and a dual linear vector space. The vector space could have any different kinds of objects. For example, as another example, you can think of the LVS to be composed of, let us say, 2 by 2 matrices. Okay, so 2 by 2 traceless or not, it doesn't matter. Let us say the LVS is composed of 2 by 2 matrices. Okay, now obviously we need a rule to define multiplication, and we need a dual linear vector space. So the dual linear vector space in this case would also be composed of 2 by 2 matrices. Okay, because we need similar kinds of objects. Of course, we really cannot multiply 2 matrices and get a number out, right? So because the multiplication of 2 by 2 matrices is also going to be a 2 by 2 matrix. So we need a rule to associate a dot product in this vector space. So the rule of dot product in this vector space would be given as the trace of A dagger B. Okay, this would be the definition of the inner product of 2 vectors. In this case, vectors are actually matrices. Now you might actually wonder, where is this coming from, right? So this seems a little arbitrary. Why assign this as the dot product? For example, why can't the dual LVS be composed of, if your LVS is composed of, let us say, 2 by 2 matrices, why can't we have a dual LVS that has, let us say, a column matrix or something like that? Or why is there this specific rule for assigning the dot product? So the reason I'm not going into this question is because there are a certain number of rules the definition of a dot product has to satisfy in the theory of linear vector spaces. So this you will understand in more detail in your mathematical physics course. There is a certain number of, for example, there is a question of linearity and things like that. So there is about 2 or 3 very simple rules that the dot product should satisfy. And it turns out that this dot product, this definition of dot product in this particular linear vector space, trace of A dagger B, satisfies all these different rules. Okay. So once you specify your rule, you should stick with that particular rule to construct the linear vector space. Of course, in ordinary Euclidean space, the dot product, so this is example 1, example 2, Euclidean space, the usual space in which 3-dimensional vectors live, the dot product, of course, of 2 vectors is A dot B, right? Which is nothing but a row vector times a column vector. Okay. Sorry. Okay. So a row vector times a column vector. All right. So this is the definition of dot product in this particular space, the second one, and there is also equivalent definitions in other linear vector spaces. There is a difference between example 1 and example 2, and not just that the example 1 where the vectors are matrices and the example 2 where the vectors are column vectors. In the first example, notice that the dual LVS is also composed of 2 by 2 matrices. Okay, of course, you have to take the Hermitian conjugate to define the dot product, but they are also 2 by 2 matrices. So every single 2 by 2 matrix that lives in the LVS is also the exact same matrix that lives in the dual LVS. So linear vector spaces in which the objects in the linear vector space and the dual vector space are the same are called self-dual. Okay. Obviously, the Euclidean space is not self-dual because column vectors and row vectors are 2 different kinds of objects. Okay. So if you have any questions, stop me at any time. You can unmute yourself and ask, or you can also type it in the chat window. I have it open. All right. So let us recast all of these things in the new language that we are learning, in the new language of vectors that we are learning, where we are representing vectors as abstract objects called kets, kets, and this lives in the linear vector space, and the corresponding bra vectors live in the dual linear vector space. So how do I define the dot product of 2 vectors? Just like I define A dot B as the row vector times the column vector, you can think of the kets as column vectors, and you can think of the bras as the row vector. So the dot product is basically a row vector times a column vector. So the dot product of 2 vectors, or the dot product is also called the inner product of 2 vectors, is accomplished by multiplying a bra with a ket. So like this. Okay, so this is the inner product of 2 vectors, beta and alpha. So this is so if you want to think of a concrete example, you can again think of the Euclidean space example where it is a row vector times a column vector. But I again stress that that is just one particular example. Okay. Now notice that if the Euclidean space were composed of complex vectors, the dot product definition should change slightly. So suppose if the complex Euclidean space, okay, where what is a complex Euclidean space? When I say A vector is AXI plus AYJ plus AZK, I mean that AX, AY, AC can be complex numbers. If that is the case, then to get a real number out, to get a number out in the dot product, I have to multiply not the row vector times the column vector, but the complex conjugate of the row vector times the column vector. Okay. So in this, the complex Euclidean space, the definition of inner product or dot product would be A dot B equals AX star, AY star, AC star times BX, BY, BZ, which would be equal to AX star BX plus AY star BY plus AZ star BZ. Okay. So if you don't have real vectors but have complex vectors, vectors that have complex coefficients, the dual vector space is not just the corresponding row vector of every vector that you see in the linear vector space, but it is the corresponding row vector of every vector that you see complex conjugate. Okay. So the objects in the dual vector space are still row vectors, but to take the dot product, you still have to take the complex conjugate of the row vector also. All right. So this also bears into quantum mechanics. So for example, when you take the inner product of 2 vectors, alpha, beta, in this particular fashion, right? You should remember that you should multiply. In general, the vectors in quantum mechanics that we will be seeing are actually complex valued vectors. So this is to be understood as the complex conjugate of the vector beta times the vector alpha. Okay. All right. So we have, up till now, we have the linear vector space, okay, which is composed of vectors with a set of basis vectors ei, and the dual linear vector space, which is composed of vectors with a set of basis vectors ei. Every vector in the linear vector space can be thought of as a linear combination of these basis vectors. And similarly, every vector in the dual vector space can be thought of as some linear combination of the dual bra vectors. Okay. And a bra times a ket would give you a number. In general, a complex number. Okay. All right. So in this, so are there any questions about this notation thus far? Any questions, any comments? Is this okay to follow, or should I pause and explain the notation again, the Dirac bracket notation?
Clear, sir.
Okay. So if there is any questions, please stop. So remember that we started by saying what is the kth component of a vector, right? Or z component of a vector or y component of a vector. And we found out that the way you extract the z component of a vector is by dotting k with a, right? In other words, if you want to understand what is the amount of vector lying in a particular direction, you simply take the dot product of the vector with that particular basis vector, right? So in this language, how does it look like? So suppose if I want the amount of vector alpha, suppose I want the amount of alpha lying in the kth direction. Okay, then I should take the dot product or inner product of the vector with the basis vector in the kth direction. The basis vector in the kth direction is of course ek, and the dot product of, just like I take k dot a to give me az, right? The extension of this would be the dot product of the kth basis vector with the vector alpha. So that is bra ek alpha. Okay. So how does this actually work? Remember that alpha can be written as ei some ai ei. Okay. So when I multiply the bra ek with alpha, remember that the dot product should always be taken with a bra and a ket. The number ai doesn't matter. So when I take ek alpha, I'm actually taking ek times alpha again is ai ai ei. Okay. So this is nothing but sum over I, ai, because the dot product does nothing to the numbers. I can pull the number out, ek ei. Okay. So this can be a little confusing the first time you see it. So if there is any questions, please stop me at this stage. So the way you take the dot product of ek and alpha is you first express alpha as a sum of all the basis vectors. That is step number 1 here. Okay. And then when you take the multiplication of the bra with the ket, you take the multiplication of this bra with a series of kets like this. So it multiplies each and every one of these ket vectors. Now I want this to be ak, right? But this seems to be an infinite sum. So remember that your ordinary basis vectors satisfy certain rules. In ijk, we have I dot I is 1, I dot j is 0, and so on and so forth. J dot j is 1 and j dot k is 0 and blah, 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 right? So this is what we mean when we say that the basis vectors are orthonormal, because they are normalized to unit length and they are all orthogonal to each other. So this is the definition of orthonormal. So we want our basis vectors also to be orthonormal, so we can define all these projections and things like that correctly. Because remember that the way you actually do projection, k dot a is easy simply because the unit vectors satisfy these properties, that I dot I is 1 and I dot j is 0 and things like that. So we better have these basis vectors that we have also satisfy orthonormality. So the way you set up orthonormality is as follows. If I take the dot product of two basis vectors ek and ei, okay, if ek is the same as ei, if k is the same as I, this has to be 1, right? Because I dot I is 1 and I dot j is 0. So I want this to be 1 if k equal to I and 0 if k is not equal to I. Okay, again, that is exactly what I have in this step above. In this, here, what I'm writing is I dot I. If I take the dot product of a unit vector with the same unit vector, I get 1. If I take the dot product of the unit vector with a different unit vector, I get 0, right? Here I'm saying, if I take the dot product of ek with ei, I should get 1 if k is the same as I, and I should get 0 if k is not the same as I. So I can club these two rules, and I can write, excuse me, EKEI is equal to delta KI. What is delta KI? Delta KI, so this is a very important piece of information. So we'll box this guy. Delta KI is called the Kronecker delta. So this is called the Kronecker delta. So delta Ki equals 1 if k equal to I and 0 if k is not equal to I. Okay, so that is the definition of Kronecker delta. Okay, so this helps me understand the concept of orthonormal vectors in this new linear vector space language. So instead of the proper definition of dot product is a row vector times a column vector in usual vector algebra. It is the multiplication of a bra vector times a ket vector in the bracket notation. A set of orthonormal vectors simply means that I dot I is 1 and I dot j is 0 in the usual Cartesian coordinate system in 3 dimensions. In the new vector space language that you're learning, it means that the inner product of a bra vector ek, a bra basis vector ek with a ket basis vector ei is equal to delta ki. So it is equal to 1 if we are talking about the same direction, and it is equal to 0 if we are talking about different directions. So let us go back to the inner product that we were evaluating, ek alpha. We found out that this is equal to sum over I, ai, ek, ei. But using this rule, we can now see that the inner product of ek and ei is nothing but delta ki. So this is ai delta ki. So yes, this is a very big sum. So if the dimension of the LBS is 135, there is 135 terms in this sum. But for all i's not equal to k, this delta ki is equal to 0. So there is only one term that is going to pop out of the sum, for which the delta ki is not equal to 0, and that is when I equals k. So when I equals k, this sum becomes just one particular term, which is ak. Okay. So again, just as k dot a, k hat dot a projects out the z component of the vector a, ek, the inner product ek alpha, projects out the kth component of, this is the kth component of alpha. In other words, it's the amount of alpha lying in the direction ek. Okay. So it is very important that our basis vectors be orthonormal. Okay. Orthonormal means they're all mutually orthogonal and they're all normalized to unit length. Okay. So there are some very simple properties of these inner products that you have to find. So there is, I'll write it by numbering it. So the first property, suppose if you have two vectors, beta and alpha, the inner product of these two vectors is beta alpha, but this will be the same as the inner product of alpha and beta complex conjugated. Okay. Why is this true? Again, think of the Euclidean space example. Suppose if I have two vectors A and B, right? I told you that in general they have complex coefficients. So A dot B is nothing but AX star, AY star, AZ star times BX, BY, BZ. So this will be equal to AX star BX plus AY star BY plus AZ star BZ. But if I compute B dot A, see, in ordinary vector algebra, A dot B and B dot A are the same, but that's only because you've been dealing with only real vectors. Vectors that have real components. So in our definition of dot product, B dot A would be BX star, BY star, BZ star times AX, AY, AZ. Again, take the row vector of the first guy, complex conjugate it, and then take the column vector of the second guy and multiply. So this would be equal to BX star AX plus blah, blah. Okay. So you can clearly see from this example that A dot B is the same as B dot A complex conjugated. Because B dot A has BX star AX, A dot B has AX star BX. So if I complex conjugate B dot A, I get BX AX star, which is exactly what A dot B has. So so this is always true that the inner product should always satisfy if this particular rule, which says that if I interchange the order of vectors that I am taking for dot product and complex conjugate, I should get the exact same answer back. Okay? Now, what if I take the inner product of a vector with itself? Right? Instead of taking inner product of beta and alpha, what if I take the inner product of alpha with alpha? As you can actually guess, this is the generalization of the concept of length of a vector. So what happens if you take the dot product of a vector with itself? So A dot A is, as you know, AX square. If I'm dealing with real vectors, AY square plus AZ square. Okay. So similarly, if I have alpha with alpha, let us actually compute it as if we don't know the answer, just for fun. The bra alpha I can write as sum over I, AI star EI. Okay, this is the bra alpha, which I can write as a linear combination of the basis vectors EI. And get alpha, I will use a different symbol, J, AJ, EJ. Okay. So I hope this is clear. I've expanded bra alpha. So I've expanded bra alpha as a linear combination of the basis vectors in the bra space, and I've expanded the ket alpha as a linear combination of the basis vectors in the ket space. This guy. So now how should I do this multiplication? Again, the AA star and AJ are just numbers. So I have two sums, 1 over I and 1 over J. And this is equal to AI star AJ times bra EI times ket EJ. Okay, but this is a set of orthonormal basis vectors. So dot product of EI and EJ is the Kronecker delta, delta IJ. So this is simply not a sum over two different indices anymore, because the only terms that will be non-zero are ones for which j equals I. So this will be ai star, j equals I means ai. So this is simply mod ai square. Okay, what is mod ai square? It's a1 square plus a2 square plus a3 square blah blah blah, which is exactly what you mean by the length of a vector, right? Ax square plus ay square plus az square. It is the absolute value squares of the components of a vector added together. Okay, so alpha dot alpha, so inner product of alpha with alpha, inner product of a vector with itself is always, see, since this is always a real number, right? Because it is not a complex number. In general, the dot product of two vectors, the way we have defined it, can also be complex because it is bx star ax and things like that. So it can be complex. But the inner product of a vector with itself, which has a special name, it is called the norm of the vector alpha. The norm is always a positive definite quantity because this is always positive definite. It cannot be negative, it cannot be complex because it is ai star ai star ai is always real. Okay, so this gives us the interpretation of the norm of the vector as some extension of the concept of the length of a vector, because the length of a vector in ordinary 3 dimensions is always a positive quantity, because it doesn't make sense to have a vector with length -2. So this is the definition of a norm of a vector. Norm of a vector is always positive, greater than or equal to 0. The only time it can be 0 is if alpha is the 0 vector. Okay, if alpha is not equal to the 0 vector, null vector, then the norm is always greater than 0. Okay, the 0 vector has no length, so the 0 vector has 0 norm, but all other vectors have a non-zero norm. So this is the definition of norm. So typically we take, sorry, we don't, this is the squared norm. So the norm is given by the square root of this. Okay, just like the length of a vector is a square root of ax square plus ay square plus az square, the norm of the vector is a square root of the inner product of the vector with itself. Okay. So I told you that the inner product of vectors should satisfy some properties. One of the properties is linearity. So suppose if I take the inner product of alpha with some combination of ket vectors b times beta plus some c times gamma vector, this has to be equal to b times alpha beta plus c times alpha gamma. Okay, so this is a simple concept of linearity. All vectors have to, how the definition of inner product should follow this. Okay, so if we were actually confused as to why we have to take, in the case of complex numbers, b dot a is anyway not real because in general it is complex. So why do you have to take the complex conjugate? If we had this question, it is simply because we want to define the norm of a vector as a positive definite quantity. Okay, if we did not take the complex conjugate, then ai, it would not be a complex conjugate, it would be ai, and ai square. If you have a complex number, z square is not in general real, right? It is complex, but z star z is always real. So that is why you have to take the complex conjugate in the definition of the dot product of two vectors. Okay, so this tells you what are the properties of a basis vector. So the properties of the basis vector, so LVS is composed of all possible kinds of vectors. Every one of these vectors can be written as a linear combination of the basis vectors. And the basis vectors should be such that they are orthonormal. Orthonormal means the length of the vector, each basis vector should be 1, and the dot product of one basis vector with a different basis vector has to be equal to 0. Okay. So are there any questions or any comments up till this stage? Any questions? You can unmute yourselves and ask. Okay. So let me, even though I don't want to spend a lot of time on this, for completeness sake, I should mention an important constructional aspect of basis vectors. So we know that basis vectors have to be orthonormal. But what if you have a bunch of vectors? Somebody gives you a bunch of vectors and they are not orthonormal. It turns out that there is a specific procedure with which you can actually convert a bunch of vectors that are not orthonormal into a bunch of vectors that are orthonormal. Okay, so let me actually work this through as an example, and then I will actually formalize this. So example. Okay. So let me take three vectors. The first vector, I will use the notation that you're already comfortable with A vector and B vector, and then I will recast this exact same thing in the bracket notation. Suppose if I have A vector, which I will write as 1, 1, 1, B vector, which I will write as 1, 1, 0, and I have a C vector, which I can write, let us say, as 1, 0, 1. Okay, I have these three vectors, A vector, B vector, and C vector. Now notice that their length is not 1. The length of A is square root of 3, the length of B is square root of 2, the length of C is square root of 2. Okay, and they're also not orthogonal to each other. You will actually find that A dot B is not 0. Okay, in other words, A dot B is 1, 1, 1, 1, 1, 0, which is 2. So neither are they normalized to unity, nor are they orthogonal to each other. So how should one construct a set of basis vectors out of them? So suppose if I'm in a three-dimensional vector space, and I give you these three vectors and I ask you, why don't you make a bunch of basis vectors out of it? Okay, there is a very specific procedure you can follow. The first step, take the first vector. Okay, step 1. Take the first vector and normalize it. Normalize A vector. The notion of normalization is very important in quantum mechanics. It simply means that out of a vector, you convert it into a vector that has unit length. Okay, how will I convert A into something that has unit length? Simple. I will simply divide A vector by the length of A vector. Suppose instead of A vector, the length of A vector is of course square root of 3. So suppose if I construct out of A and A prime, which is 1 over root 3, 1, 1, 1. I should not change, when I do the normalization, I should not change the relative weights of the components. Okay, but I will simply divide this vector by the length of the vector. Now the length of A prime is 1. Okay, as you can easily check. So suppose if I divide it by the square root of A dot A, I get something that is normalized to unity. So this is the procedure of normalization of a vector. If there's any questions about this, please ask, because we'll be using this over and over in quantum mechanics. If you work with non-normalized wave functions in quantum mechanics, then you will get nonsensical answers. So you should be very careful. Okay, so that is, I have constructed, my job is to construct three orthonormal vectors. I have constructed first vector, that is normal. Now I have to construct a second vector, and then second vector should be normalized to unity, but it should also be orthogonal to A prime rather. So how will I make sure that a vector is orthogonal to another vector? So let us say that I have A. So let us call this some other vector, not A. Let us call this some D vector, which is dxi plus dyj plus dzk. And out of this D vector, I want to construct a new vector that is perpendicular to the z direction. Now, obviously, D vector is not perpendicular to the z direction because it has a z component, right? It lies along z. But suppose if D vector did not have any z component, it will be perpendicular to z because I and j are perpendicular to z. So I need a way of subtracting out the z component of D. I know how to extract the z component of D. That is simply k dot d. Okay. K dot d times k vector is the z component of d. K dot d is dz. Dz times k hat is the z component of d. So if I simply take d and subtract out the z component of d, I get something that is perpendicular to the z component, right? So this is exactly what I would do to construct a new vector that is perpendicular to A prime. So I will take B and I will subtract out the amount of B lying in the A direction, A prime direction. Okay, that is all. This is exactly the same as what I have done before. I have taken B. Now B is not perpendicular to A prime because B has components along the A prime direction. So if I know exactly how much of B lies along A prime, which is A prime dot B, I can subtract off this amount of B that lies along A prime, and whatever is remaining will be perpendicular to A prime, obviously. So what is this? The vector B in our example, is 110. So this is 110 minus, what is A prime dot B? A prime is this guy. So let us actually work out A prime dot B separately and then do this exercise. So A prime dot B is 1 over root 3, 1, 1, 1, row vector, times B, which is 1, 1, 0. So this is equal to 1 over root 3 times 1 plus 1, which is 2 over root 3. The dot product has to be a number. So B minus A prime dot B times A prime would be 110 minus 2 over root 3, which is A prime dot B, times A prime, which is 1 over root 3 times 111. Okay, so this whole thing is given by 110 minus, what is this? So there is 2 factors of square root of 3. So this is 2/3, 2/3, and 2/3. So this is 1 minus 2/3 is 1/3, 1/3. This is minus 2/3. So the vector B minus A prime dot B times A prime is given by 1/3 times 1, 1 minus 2. So we have achieved half of our goal. We have constructed a second vector that is perpendicular to the first vector. But this vector has to be again of unit length if it is to serve as a basis vector. So I have to divide this vector by the length of this vector. So I have to normalize this. And if I normalize this, I can find a new vector B prime. So the length of this vector is, what is the square root of 19 plus 19 plus 49, right? That is square root of 6 over 3. So if I divide this, the 3 would cancel. So I would have, I think, 1 over root 6, 1, 1 minus 2. Now you can check yourselves that B prime dot A prime would, so what to show? So if our construction is right, this has to be 0. So b prime has a square root of 6, a prime has a square root of 3. This is 1, 1 minus 2 times 1, 1, 1, which is properly 0. So there is no component of b prime that lies along a prime. So we have constructed two vectors. We have specifically subtracted off the amount of b that lies along a prime to construct a vector that is orthogonal to a prime, and we've also normalized it to make sure its length is 1. Now we have to construct the third vector. So step 3. What is step 3? I have the third vector, which is c. Now I have to make sure that c is perpendicular to both a prime and b prime. Okay, so the way I would do this is I would take the vector c and I would subtract off all components of c along a prime, and I would subtract off all components of c along b prime. So a prime dot c times a prime minus b prime dot c times b prime. Okay. So this ensures if I subtract off all components of c along a prime, it makes sure that this vector is orthogonal to a prime. If I subtract off all components of c along b prime, it makes sure that this vector is orthogonal to b prime also. Now I will get some vector, and then you normalize that vector, and you will get a third vector. Okay. Now your homework is to complete this exercise. I'll also put it as a tutorial problem, and find c prime. Okay. Then you would have 3 new vectors, a prime, b prime, and c prime, constructed out of the set A, B, and C. A, B, C were neither orthogonal to each other, nor normalized to unity, but A prime, B prime, C prime are normalized to unity and are mutually orthogonal, and therefore can serve as basis vectors in the 3-dimensional linear vector space. So instead of using I1 0 0 0 1 0 0 0 1, I can also use A prime, B prime, C prime, which are mutually orthogonal to each other and normalized to unity. So I will recast these same steps in the language of the Dirac bracket notation. So step 1, so the question is, suppose if we have a bunch of vectors EI, and these EI are not orthonormal, then how would you construct a bunch of EI primes that are orthonormal? So the first step is to normalize the first vector. So you take the first vector and you divide the first vector by the length of the first vector. Okay, so let us call this E1 prime. Just like we normalized A to get a vector that is of unit length. The second step is to take the second vector and subtract off all components of the second vector that lie along the direction E1 prime. To do that, I have to take the dot product of E1 prime okay. Then I would have to normalize this to get E2 prime. Okay. Then the third step would be to take the third vector and subtract off all components of the third vector along the first vector and the second vector. And then normalize this to get E3 prime. And then keep going. Take the fourth vector, subtract off all the components along E1 prime, E2 prime, and E3 prime, and whatever you get normalized, that will give you the fourth vector, and so on and so forth. And in this way, you can construct the set EI prime such that EI prime EJ prime equals delta IJ. And if EI prime EJ prime is equal to delta IJ, they can serve as basis vectors. And I can write any vector alpha in this basis as sum over the basis vectors. This procedure of constructing a bunch of orthonormal vectors from vectors that are neither orthogonal nor normalized to unity, this procedure is called Gram-Schmidt, named after two mathematicians, procedure. Okay. This is very straightforward to do. Sometimes if you simply look at this in the bracket notation, it can be a little confusing, but if you always go back and look at a concrete example, it should be rather straightforward to understand. Okay, we will stop here at the construction of these basis vectors, and we will continue our discussion in the next lecture. So are there any questions about any of these things?